minimize that. So, acid-base properties of salt solutions. Don't write this first stuff down. In the past, when I've done this lesson, I sometimes didn't get to the note on the relationship between Ka and Kb for a conjugate acid-base pair. But that's what this particular lesson here is describing. And I'm not going to worry about doing this first little equilibrium thing, but it kind of, well, I can go through it. What we've got here is I'm asking for the relationship, which remember is going to be, let me grab a pen here. This is going to work. It's going to be what? The concentration of H3O plus, right, times the concentration of F minus over liquid we don't count, concentration of HF. All right, does that sound familiar to everybody? And then if I now look at the F minus as a conjugate base, because here it's behaving as an acid, and here it's this conjugate base, it's going to behave as a base, it's going to produce some OH. So if I write here again, HF times the OH minus over F minus, again, the water isn't included. What I've asked you to do in this little sense is take the Ka and multiply it by the Kb, right? And actually, I'll do this over in the corner here. So if I now take the Ka times the Kb, H3O plus, that's the Ka, F minus over HF, and I multiply it by the Kb over here, HF times OH minus, and then that is F minus. You'll notice here, I've got things that I can easily cancel away. F minus there, F minus there, HF there, HF there. So if I take a Ka and I multiply it by its conjugate base, I end up getting H3O plus times OH minus, which is equal to Kw. Now what did that prove? That proves that Ka times Kb is equal to Kw. And that's what I showed you very quickly at the end the other day. No need to write that down. We actually did that lesson already, okay? So that's what the purpose of that little exercise was for. It's not a big deal, but it essentially relates the Ka on one side to the Kb on the other side, and if you multiply them, you end up with 1.0 times 10 to the minus 14, which is the Kw. All right, and that allows us to think in terms of, okay, what do we have? Do we have an acid, or do we have its conjugate base? Okay, so at this point, I even did these examples already. So if we know the Ka for an acid, we can determine the Kb for its conjugate base and vice versa, and we did these examples, and I'm not going to do them again, okay? We just have to rearrange the equation and solve. We did that example, oh, I don't know if we did that example, but we might have done this one. Determine the pH for 0.02 moles per liter of a solution of acetate ions. Actually, I might just roll through that one for a second. You don't have to write it down. So what we're saying here is, look at, this is acetate. And the acetate ion is the conjugate base, all right? It's the conjugate base of acetic acid. If I didn't have my little table, I could calculate what that Kb was if I knew what the Ka is. But I have my little table. So I can easily just write it down as being a Kb. Why? Because it's a base. Even though it came from an acid, it is a base. So if I take a look at the conjugate base for acetic acid, there it is there, 5.6 times 10 to the minus 10. So 5.6 times 10 to the minus 10. And because it's behaving as a base, I'm going to use the base equation. OH minus the root of Kb times the original concentration of the base. Now, there it is right there. There it is right there. It's going to be the root of 5.6 times 10 to the minus 10, and then again times 0.020. And I believe we did that value. We did that. So what I'm saying here is, now we have to look at the question very carefully and we have to ask ourselves, are we dealing with an acid, or are we dealing with its conjugate base, or are we dealing with a base, or are we dealing with the conjugate acid? And that's what I'm going to show you today, how you recognize what we're dealing with so you can pick the right Ka or Kb, and then you can do the right math, okay? Because now it gets a little blurry, because we have acids and bases and conjugate acids and conjugate bases. But we'll get it straightened away. Now, I do want, I assigned those the other day. I do want you to write this down. Now, this is something that I've kind of made up myself. And it's going to look like this. And I'm trying to do it on the computer. It's two scales that I'm going to be relating between, a Ka scale and a Kb scale. And I've made it look this way so that we can have extreme edges. It's almost like a pH scale, all right? And in actual fact, when you go to university, you're not going to be given the Kas and Kbs like this as a big times 10 to the negative whatever. You're going to be given it as something called the pKa, where they take the power off of the Kas and Kbs, just like they take the power off of the H3O plus to get pH. I'm not going to deal with pKas and pKbs with you guys, but you will see it in the future. So what I want to do in the middle of my little Ka scale here, and I'll let you kind of get caught up. We already know the relationship. We know that Ka times Kb is equal to Kw, 10 to the minus 14. But I just want to stress the relationship now in a graphical method that hopefully allows you to kind of internalize this information a little better. At the very center of both of my scales, I'm going to have 10 to the negative 7, just like the center of my pH scale where I have a concentration of 10 to the negative 7. But now this isn't a pH or even an H3O plus. This is the size of that Ka or Kb. So it's not going to be talking about strong acids and strong bases, but, well, actually, no, it is. It's still going to be talking about strong acids and strong bases, but it isn't necessarily going to mean the pH that we get. It has to do with their strengths. Down here on the Kb scale, I'm also going to have a 10 to the negative 7. And up here on the Ka scale, I just want to make sure I do this right so I don't have to do it. I'm going to have a 10 to the negative 14. And all the way down here on my Ka scale, I'm going to have a 10 to the 0. In other words, it's going to look a lot like a pH scale. Same thing on my Kb one, 10 to the negative 14, 10 to the 0. And I'm hoping you got the idea that I've got these lines above and below each other, because I'm going to be crossing over. When we turn an acid into a base, we're going to take the Ka and we're going to figure out where the Kb is going to be. All right? So right here in the middle, both of these, well, actually, let's go to the extreme. 10 to the negative 14 for a Ka, how would you describe that acid in terms of its strength? If it had a Ka that had a power of 10, that was 10 to the negative 14, how would you describe that acid in terms of strength? Very weak, super weak, all right? So I'm going to put over here, I'm going to put super weak. And that's true down here with the base. If I have a base that is also way down there at 10 to the negative 14, it's super weak. And it's a super weak acid. I'll put that on the end there. And this is a super weak base. Okay? And if I were to go to the opposite end of the scale, even beyond 10 to the 0, where I'd have here 10 to the 1 and 10 to the 2, if we have a positive power of 10, how would you describe that acid? It's strong. Strong acid, and down here we've got strong base. Okay? So we've got strong and we've got super weak. And so in the middle, is where we stick our weak guys. And I'm going to just, to give it kind of a descriptor, I'm going to call it moderately weak. You know what I mean? Like it's not super weak and it's not strong, but it's kind of weakish. So I'm going to call this mod weak. Mod weak. That's funny. People could dress, now forget about it. All right. Moderately weak acid. And in the middle, moderately weak base. And for anything that is down here in that moderately weak, because our assumption, remember, is 100. So if we have anything that's like around 10 to the negative 3, our assumption's going to be good. Anything down here, we're going to be using our shortcuts for the strengths of the acids and the bases, right? Anything that's in the middle here, we'd have to solve a quadratic. And anything that's way out here in the strong, they all fall off, all right? So let me change the color here for a moment, and let's now talk about a particular one. Let's talk about HF. So if you have your pages out, please have them out so you can supply me with some numbers. And I'm going to just quickly take a look as well, and I'm going to deal with HF to begin with. And if I track down my HF, there it is there, 3.5 times 10 to the minus 4. So if I've got like minus 1, minus 2, minus 3, minus 4, I'm right in there somewhere, all right? So this is HF, and it's 3.5 times 10 to the minus 4. It's up to you if you want it to be colorful or not. I would describe that as a moderately weak acid. It's heading towards strongish, but I wouldn't say it's strong in any way. If I was dealing with 0.1 moles per liter, my assumption would be good. I'd be using my weak acid equation. Let's now take a look at what the conjugate base is going to be for HF. Well, we could do the calculation, but our page already has it. So I'm going to just work my way across HF, and I get 2.9 times 10 to the minus 11. Now, because of the calculation, Ka times Kb equals Kw, it's actually going to be the exact opposite length from that center line to its conjugate base. It always will be that way, because we're always going to be using that equation Ka times Kb equals Kw, and that always gives you the same relationship that cuts across and gives you the conjugate base, all right? And I'm looking at the number, and I got 2.9 times 10 to the minus 11, 2.9 times 10 to the minus 11. So look at here, a moderately weak acid that has an exponent that's greater than, not greater than negative 7, but closer to 0, right, than negative 7, stronger than negative 7, becomes a moderately weaker base. All right? And that's why we call this an acid, because it starts out here as being stronger than its weaker base that it forms. That's why it falls under acid categories. Okay? And I often like to just draw a line to kind of visually represent the fact that we cut across. Hey, I'm impressed with my relatively straight line. I'm very pleased with that. Hey, this is tough, this crazy device. Let's do another one where we take a look at a base, a moderately weak base. And on my page from the past, I used NH3. So let's use NH3. So I'm looking at ammonia, NH3. It's going to be on the base side, 1.8 times 10 to the minus 5. So that's minus 7, right? Minus 6, minus 5, somewhere in here, not quite as far over. I'm going to use white again because I'm going to be noting some other things in a moment. And that is NH3, and that is 1.8 times 10 to the minus 5. And notice that it's closer to 0 than minus 7. That's why it goes on the base side. It's a base. Its base properties are a little stronger than its acid properties. That's why it's better at being a base. If I do the same, and it's going to be, the conjugate acid is going to cut across. It always does. That's going to be NH4 plus. It is going to cut completely across there. I'm going to check its acid properties, and it is going to be in the 10 to the negative, what are we at here? 8, 9, 10, somewhere close to 10. And what is the number? I've lost it. Somebody have it there? 5.6 times 10 to the negative 10. Okay? So, what have we got here? If I've got something that's a moderately weak acid, it becomes a conjugate base that's also moderately weak. It's a little weaker. It always gets a little weaker. If I have a moderately weak base, then its conjugate acid will also be moderately weak, and it'll be weaker on the opposite side of -7 every time. Okay? Let's now take a look at how to deal with our strong ones, because the moderately weak ones make some good sense. But let's think about how it works with a strong one. So if I have a strong acid over here, and I'm now going to change colors one more time here, because I just don't want it to kind of mix in. But let's say way out here, I'm looking at like HCl. And I'm not even going to worry about the number. Well, I guess I could. Do I have hydrochloric acid on there? Hydrochloric acid, 1 times 10 to the 6. So I'm going to put this way out here. I'm going to put HCl, and I'm going to put 1 times 10 to the 6. Super strong. All the H's are falling off, right? Where is its conjugate base going to be? Well, what's the value for the conjugate base? What is the conjugate base of HCl? So I've got here Cl minus 1.0 times 10 to the negative 20. How would you describe that as being a base? How is the chloride as being a base? Terrible. It is like the weakest, wimpiest thing ever at being a base. If we relate it back to our game that we were talking about at taking the H's and that type of thing, chloride absolutely sucks. You put chloride in a solution, and it's not going to take an H plus from anything. If we put something in solution and it really doesn't do anything, and it's not going to do anything, we have a word for that. I've used it maybe already this term, but I definitely talked about it last year. When you put something in the water and we did our net ionic equations and it doesn't do anything, it just kind of gets canceled away, what kind of an ion did we describe that as? Yeah, so way down here at super weak, at beyond -14, these are spectators, spectator ions. These guys do nothing. They go in the water, forget about it. So anything that's strong, like nitric acid, its conjugate base, nitrate, is a spectator. It doesn't do anything. It's not going to get involved in taking H pluses from anyone. All right? So we dismiss them. If we have those in the water, we dismiss them. Let's take a look at a really strong base example. And the easiest is NaOH. Now, I don't even have a number for NaOH. It's not on here. And that's because it's an ionic hydroxide. All the OHs fall off. They're super strong. Let's just say the Kv is big. You see what I mean? I'm just going to say that it's really big. It's going to have them all fall off. Which means, where does the conjugate base sit? Or sorry, conjugate acid. Yeah, way over here. What is the conjugate acid of an NaOH? The Na. Very good. Na plus. Technically, Na, I guess, could go up to a water and try to steal an OH and thus release an H plus into the water to make it acidic. That's theoretically what could happen, but it doesn't, because it's such a weakling, it doesn't happen. So how would you describe the base ability, the acid ability of Na plus? Super weak, so crazy weak that it isn't going to do anything. It is also a spectator, all right? Any of the conjugate acid or bases that come from strong acid or bases are spectator ions. They don't do anything. So moderately weak makes a moderately weak. Moderately weak base makes a moderately weak acid. A strong acid makes a spectator ion. It does nothing. And a strong base also makes a spectator ion. So now we're ready to start looking at what happens when we deal with some of these salts. Because here's the questions we have to ask. When the salt falls apart, what are we left with in the water? What is Na plus? Well, Na plus is a spectator. It does nothing. It came from sodium hydroxide. What's an F minus? An F minus is a moderately weak base that came from HF. And now we can start thinking it through and doing the mathematics. Okay, so we don't need to write this down. We're going to answer this in a moment. When salts dissolve in water, they dissociate into individual ions, and they may or may not exchange an H plus in a Bronsted-Lowry acid-base reaction. Therefore, they can affect the pH of a solution. NaCl is neutral, sodium carbonate is basic, ammonium chloride is acidic, and we'll explain that right now. So let's write down hydrolysis to begin with. We have been using this equation. We were introduced to it last week. When I introduced to you the concept of weak acids and weak bases, and Bronsted-Lowry acids and Bronsted-Lowry bases, I talked to you about a reaction that happens between the weak acid in water and the weak base in water. But I didn't give it a name. I just called it a Bronsted-Lowry acid-base reaction. There is a technical name for this little reaction, and it's called hydrolysis. Hydrolysis simply means the breaking apart of water, and that breaking apart of water is the reaction that takes place with our weak acid or our weak base. So nothing new on that slide. What's that? Besides the definition hydrolysis that defines that little reaction. Okay? And it can be done by a moderately weak acid or a moderately weak base. Okay? Again, let's not write right away. I just want to take a look at the slides. Salts that form neutral solutions, yeah, you can write this down. And I'm actually going to do the examples here with you. Cations of a strong base. We've already encountered those in my little crisscross diagrams. The cations in a strong base are what we call spectators. Group 1 or 2 cations. Some examples, Na plus, K plus, etc., etc. Those are all spectators. anions of strong acids. We already encountered those as well. I've already taught you that those guys also make spectators, right? If they're from strong acids, these are also spectators. They do nothing. Why? Because they came from a strong acid. I always want you to think, when you encounter ions, think about where they came from. And what I mean by that is, what acid or base did they come from? That's what we're really doing here. We're taking the salt, and we're going to break it apart, and we're going to say, where did you guys come from? What acid and what kind of base did you come from? And then we'll make the logical statements needed to answer the question. So my example is going to be here, NaCl. Okay? Now, when you get a salt, if I ask you, could you tell me if it's going to be acidic, basic, or neutral? The first thing you have to do, all right, number one, is do a dissociation reaction. I'm going to spell dissociation wrong, so I'm just going to put this. Remember, dissociation reactions are simply breaking the ions apart. NaCl aqueous is going to produce Na plus Cl minus. All right? So break the ions apart. Dissociation is completely different than hydrolysis. Dissociation is just the ions falling apart. Hydrolysis is, does it react with water? Do the ions react with water? So now that you've got your ions, let's take a look at each of those ions. Na plus. Exactly. It's a spectator. I just want to just put a little more information here. This is the super weak conjugate acid because it came from a base. Yeah, remember it cut across? It's a super weak conjugate acid. Therefore, it's a spectator. Nothing. If it's a spectator, therefore, no hydrolysis. And if you can't spell, you have to say it that way. Hydrolysis. And that's a Y. Yeah, that's the ugliest hydrolysis that you've ever seen. But I'm not fixing it because I'm recording. Does it make sense, though? Sodium came from sodium hydroxide. Sodium is a super weak conjugate something, and it is not going to react with the water whatsoever. Cl minus. How would we describe it if I wanted to write a statement like this? How would I describe Cl minus? Super weak conjugate base, spectator, no hydrolysis. Does that make sense? Super weak means they're not going to react with the water whatsoever. Super weak conjugate base, therefore spectator, therefore no hydrolysis. If there's no hydrolysis whatsoever, then there's no OHs or no H3O pluses formed. It's neutral. Therefore neutral. Okay? Now let's analyze some other acids and bases or other salts that have some moderately weak guys in it. That's essentially what we're doing. Okay. Yeah, ignore that writing underneath there. Salts, yep. What are we going back here for? What are we doing? Really? Oh. This pause is for Anthony McCreary. What's going on the internet, by the way? Okay. Yeah, go ahead and write that. And I'm going to cheat and look at my example here because I want to write the example down. Oh, come on. My example's on the next page. Just write that, and then I will make up an example. Sounds like fun. So the example I'm going to do here is ammonium chloride. All right? I've already said the first thing you have to do is dissociate it. I'm not going to rewrite the dissociation. Let's just go straight from here. So let's say we have some ammonium chloride aqueous. We're going to dissociate that. NH4 plus Cl minus. Let's analyze now our ions, and I'm going to actually start with the Cl minus, all right? Cl minus, well, we've already encountered this guy. Comes from HCl. HCl is strong, so Cl is super weak. Super weak. And I don't even care if it's a conjugate acid or a base at this point. If it's super weak, it's doing nothing. So I can actually shorten this up. Therefore, what is it? Spectator. And therefore, how is it going to interact with water? It isn't. No hydrolysis. Now we analyze the other ion, NH4 plus. Well, where does NH4 plus come from? It comes from NH3. And if we check our sheet, they're kind of moderate. They're in the middle. So that means this is a moderate conjugate what? Now this is the hardest part. Is this an acid or a base? It's an acid. It's a conjugate acid. It's a moderate conjugate acid. Therefore, it's not a spectator. Yes, hydrolysis. And I'm going to just quickly write the hydrolysis reaction. NH4 plus water. It is an equilibrium. What am I going to get? An NH3. And here's the important part. I get the H3O plus. I get an H3O plus, which means right from here, what am I going to say about this particular solution? It's acidic. It's going to make it slightly acidic. Therefore, acidic. And that's what it's all about right there. which means if I had given you a concentration, let's say 0.02 molar, I would use the acid equation to figure out what the pH is. Because I would have this hydrolysis, and therefore I would simply stick it in the acid equation, the weak acid equation, and I'd get its pH. We'll do that quickly at the end. Hopefully we got enough time. Okay? All right. Let's move on. Okay, ignore all this extra. Oh, how's it going back there? We're good? All right. We did that example. Let's talk about these guys here. And let's just, right there. And the example that I will do here is KNO2, not KNO3, right? Because nitrate is one of those that comes from a, what's that? Oh, because it's different than the, no, I changed it up. I knew that it wasn't one the what. What did I use, HF before? Sorry, KCN? Oh, that's no fun. Let's do KNO3. Oh, goodness gracious. Just scribble it out. You know you want to. Just scribble it. Like, just with pen. Just scribble. Oh. I didn't actually change it to cause you discomfort, but that is a little bonus on the side. It's kind of entertaining. So, if you're given a salt, right, dissociate it. Don't even, if I'm asking, is it going to produce an acid or a base or be neutral? Dissociate it. So that's aqueous. That's going to produce a K plus and an NO2 minus. It doesn't matter the order, but I'm drawn to the K plus because where did the K come from if it was an acid or a base? The K is going to come from KOH, right? We have to be thinking that way. The K, the only way it can be an acid or a base is to come from KOH. KOH is one of those ionic ones that dissolve like crazy, so that's strong. So what is K? What is K? Super weak conjugate acid. Spectator, no hydrolysis. Super weak conjugate acid, spectator, no hydrolysis. NO2 minus. You could confuse this with an NO3. You could be forgetting about your list of weak acids and strong acids and, oh my goodness, so many things. Go to this piece of paper. You could even forget about whether we're dealing with a conjugate, blah, 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 blah. Go to the piece of paper and find NO2 minus and tell me what side it's on. Is it on the acid side or is it on the base side? Here I'm really breaking it down, the simplest of simple. You're doing this problem, you forget all this crisscross thing, you get an NO2, and you go, oh my goodness, what is this behaving at? You find it, and which side did you find it on? The base side. And what's the power of 10 of its KB? 10 to the negative, that's moderately weak, right? It's in that middle. That's a moderately weak base. Whether it's a conjugate or not, I really don't care. It did come from nitrous acid, right? But who cares? If you're writing the test and you're kind of struggling, you find that and you're going to find that that's a moderately weak base. Whether you put conjugate in there or not, I don't care. It's a true statement. So if you know where your moderately comes in with a power of 10, you're doing just fine. Therefore, yes, hydrolysis. As soon as you say it's moderately weak, right, you've got hydrolysis, NO2 minus plus H2O. Let's complete this. Because it's behaving as a base, what am I getting as products here? Jason? Oh, NO3 plus, think it through. What did you do there? You did something goofy. HNO2, that's a Monday morning gap right there. Well, that's coming off of the NH3. That's okay. HNO2 plus OH minus, and therefore, this is going to be what? Basic. Oops, that's arrows in a terrible spot. Basic. All right? Because we end up with that. Yeah, it says basic. All right? Okay? Let's do a couple more. We're going to go? Yeah, we don't care about that writing. Don't care about that example. You can write that down. To where? I'm hoping you can.
Okay, go ahead.
No, I'm going to help you.
No, I'm fine.
I want to change my example again. All right, you're right, we won't. Am I doing NH4CN? All right, I'll do NH4CN. So let's say I've got something like NH4CN. Same thing, break it apart into its ions. So let's dissociate it. NH4 plus CN minus. Ammonium cyanide is what that is. Well, let's analyze each of the ions just as we did before. NH4 plus. Again, let's say that we're overwhelmed. We don't know where it's coming from anymore. We don't know whether they're acids or bases. We don't know what we're thinking. We're going to this page. You're finding NH4 plus and you're telling me what side it's on and what it's going to behave as. Yeah, Albert? And how would you describe it? Strong, moderately weak, blah, blah, blah. Moderately weak. So we're going with a mod, weak, acid, and therefore, yes, hydrolysis. And let's quickly write the hydrolysis. I'm going to try to squeeze this in because I want to get both of them on the page. So that means NH4 plus H2O is going to get me NH3 plus H3O plus. And I would like the Ka to that, if someone could tell me that, if it's nearby. 1.6? 5.6? 5.6 times 10 to the negative 10. All right? And you might say, hey, it's going to be acidic. Well, hold on. We got to take a look at the CN this time. CN minus. Again, we're overwhelmed, too much stuff. Go to the page. What side is it on? What's it behaving as? It's a base, right? And I'm thinking it's a moderately weak base. It's hanging around 10 to the, well, what is the number? That's still a stronger base, but it's still not, you know what I mean, in the strong region. We're still calling that moderately weak. 10 to the 0 or 10 to the 1 when it's not a negative. Yep. Moderately weak base. Therefore, yes, hydrolysis. Let's write the hydrolysis reaction. Cn minus plus H2O. What's it going to be? This is really conjugate acid base swapping, right? We're really reviewing our conjugate acid base stuff. HCN plus OH minus. Jason picks it out of the fire from that first gas. That's okay. And what's the KB? We had 10 to the negative 5. I just need the front numbers. 2.0. 2.0 times 10 to the negative 5. All right. What do we have here? Is it going to present itself as being acidic, or is it going to present itself as being basic? What do you think? What do you think? It's obvious. Just look at the numbers. It comes from the numbers. Yeah, basic. Why? Because the Kb is bigger than the Ka, and which means cyanide is better at being a base than NH4 is at being an acid, so it dominates. It's going to be acidic. Now that calculation is difficult to do, and I won't make you do a calculation like that because you've got two equilibrium happening at the same time. But we can qualitatively say, because the Kb is greater than the Ka, therefore it's going to be a basic solution. Okay? Make sense? So that's if we don't have spectators in there and we've got a couple of moderately weak acid and moderately weak bases. All right, that's that. That's not a big deal. Yeah, we've already wrote that down. Predict whether that's going to be acid-base neutral, determine the pH. I do want to do this example here, you bet. So let's work through this one. This just has an add-on. What would the pH be? So all we've got to do is determine whether it's going to be a moderately weak acid or moderately weak base, and then just apply the appropriate equation. And on a test, this is the way I present this type of question. I make you think through how it's going to behave, and then we do the calculation. Dissociate it first. Take a look at the ions. Spectator, not a spectator. You can write out the hydrolysis if it happens, so we can predict whether it's acidic or basic or neutral. Then we move on to the next question. You can go ahead, you know, without me here, like you can finish it off. Na plus. What is it? It's a spectator. You know what? If you just want to write down spectator, that is spectator. If you want to spell it properly, spector. Spectre. That's funny. That's a bad guy in a James Bond movie at the beginning anyway. Spectator. All right. Anyway, if you just want to write that down, that's good. It's good enough. All right? Done. No hydrolysis. I understand that. NH3 is a spectator as well. Sorry, hey, NO3, spectator as well. It comes from HNO3, nitric acid, which is strong. Spectator. Therefore, what kind of a pH is it going to have if they're both spectators? 7, so neutral. Which makes part B a trick question. It doesn't matter how much of that stuff we have in it. What's the pH going to be? 7. Oh, trick question. No calculation needed. Again, you don't have to write down all that conjugate, blah, blah, blah. When it's weak, I do want you to write down that it's moderately weak acid or a moderately weak base. I do want you to write that. But if you go straight to spectator, that's fine. This one won't be. If you want to just put number 2 and just put KNO2 this time, same question as number 1, it is. The exact same numbers. It's the exact same thing. It's just now I'm dealing with KNO2. So the numbers are the same. What's K plus? How is it going to behave in the water? Spectator comes from KOH. NO2. Again, if you're not sure where it comes from, yeah, it's a base. It's a moderately weak base. Yes. Hydrolysis. NO2 minus plus H2O. And I'm just looking at the time, HNO2, so I'm going to just put down what we got, OH minus. Which means I'm going to use OH minus is equal to KB times the concentration of that base, because it's a base. I just need, and I'm running out of space here, so I'll put it off the side, I need the concentration of NO2 minus. How much NO2 minus is going to be in that water? 0.10, because there's only one NO2 for each one of these KNO2s, right? So this is that classic break the ions apart. I could put 1 to 1, but I don't need to. 0.10 molar times 1 to 1, right? There's one NO2 in each one of these. So, root, whoa, that's a terrible root sign. What's the KB for NO2? Somebody have it? 10 to the negative 11 times 0.10, take the square root, get the OH minus, take the negative log, get the POH, subtract from 14 and get the pH. This is where, don't clear your calculators, right? Just keep pounding through those answers. I'll take the POH. I don't even need that middle number. If you got the POH, that'd be great. Because in the end, I got to get pH. 5.8, that's the POH. POH, 5.8. One more decimal would have been nice, but it doesn't matter. And therefore, subtract from 14, what do you got? 8.2? 8.2. We predicted moderately weak base, and we're in the weak base territory. Fabulous. On the good old pH scale. Okay? So when you're given a salt, break it apart, analyze each ion, and then go ahead and solve for whatever it's behaving as. whether it's behaving as an acid or a base. And this one is going to be the other way. I'm not going to do that example. It's going to be a moderately weak whatever. There are some questions right there for you. And I've got one more little example, but I'll use it tomorrow as kind of a review. So we'll do that last little example as a little kind of summary and review for tomorrow. Sorry, I'm going to move that out of the way.